So welcome back. We'll start the afternoon session of today with Murad Alim, who's going to be talking about non-perturbative quantum geometry and resurgence in Bps structures.
Great, thanks a lot for the introduction. Also, thanks for the organizers for inviting me to speak here. So it's been a very exciting workshop for me. So I should admit I'm fairly new to working on resurgence. I've been following what's going on, but really working on this started a little more than a year ago. And it's been very exciting because resurgence turned out to connect many things that I had been working on earlier in a very nice way. And yeah, so what I want to talk about today is based on these works from the last 2 years, maybe. So 2 of these, my work, and then most of the talk will be probably addressing a paper with Arpan Saha, who used to be a postdoc in Hamburg, is now IC Math in Madrid, Jörg Teschner from Hamburg, and Iván Tulli, who's a postdoc in Hamburg. As well, I'll touch just briefly on a more recent paper with Lotte Hollands from Heriot-Watt University in Edinburgh, as well as Iván Tulli from Hamburg. Okay, so I work on geometry of string theory and quantum field theories. So I'm going to try to explain these things. So I understand that the background of the audience is very diverse, and this is why I would spend maybe a lot of time on the motivation introduction, and also put some larger context of my research interests and where the things that I'll be talking about fit in there, and then only address sort of technical results later on, and encourage you then to look at some of the preprints if you're interested in more details. So there'll be more overview than technical details in this talk. Okay, so the motivation, so the area that I'm working on, so it's really the connection between math and physics that is obtained from thinking about physical theories, not as isolated objects, but really thinking about families of physical theories. And the family, so would be like theories sharing the same parameter space, and parameter spaces can be thought of as the spaces of couplings, masses, and so on. And very interesting relationship to mathematics comes from thinking about these parameter spaces as moduli spaces of some geometry. So an early example of this is the work of Seiberg and Witten, where there is a 4-dimensional n equals 2 SU2 theory. Together with its parameter space, it was realized that the theory only looks like what you think it is in a limiting point in this parameter space. But other than that, it may look very different. So this is just a generic picture that the underlying parameter spaces will have some singularities or some boundary points. Usually the interesting physics is sitting at these boundary points. And then you'll have different regions of these parameter spaces where you have a completely different theory. So if you think of Lagrangian defining this theory with some gauge group and matter content, in some other region it will be completely different. So what was also realized by Seiberg and Witten is that there is phenomena attached to this, not just that in limiting regions you have different theories, but there is also, if you think of some spectrum of states associated to this family of theories, then there is some jumping phenomena. There's really spectra can be infinite in some regions, and then they become finite in other regions, or infinite in a different way, and these became known as wall-crossing problems. So of course, on the math side, the translation of Seiberg-Witten was that the data, or the relevant data for their work of this theory, was captured by deformations of an elliptic curve. And maybe to tell you what this data of the objects that undergo wall crossing, this is maybe more recent to understand what is really attached to the elliptic curve that causes this. Okay, so this interaction is beneficial for both sides, so it's not just from one side going to the other. So what we often find is that a natural way to organize mathematical invariants is in terms of what we would call physically a partition function. So mathematically, we just formal sums where you have some formal variables, and then you enumerate possibly infinitely many variables, and you find that the natural way, or a best way to organize these, is in terms of something that can be matched to physical partition functions. Examples in my talk would be what are called Gromov-Witten invariants. So it will be specifically in my talk, there will be Gromov-Witten invariants attached to Calabi-Yau threefolds. It's a class of real 6-dimensional manifolds, so complex 3-dimensional. And these invariants are organized in terms of a perturbative or asymptotic series, where the summation is given in terms of the genus of a Riemann surface. There's another type of invariants attached to the same spaces, Calabi-Yau threefolds, and these are called Donaldson-Thomas invariants, and these are concerned with subspaces of a given space. So subspaces and interesting mathematical structures that can live on these. From a physical point of view, the two invariants are very different. So one of them is just fixing your target and then looking at all ways, all possible ways you can map into it from different genera. So there will be the perturbative formulation. The other thing is just fixing the target and then starting asking, okay, what are interesting sub-objects in this target? So this is would be physically corresponding to a non-perturbative formulation because there is no summation over some parameter involved there. Okay, and then the surprise is that apart from the physical partition functions that you get if you organize these mathematical invariants in terms of partition functions, there's often a different geometric quantization problem that arises. And I'll give you some examples, hopefully, in the talk here. And of course, the interplay between understanding why these things arise and how they arise and how perturbative, non-perturbative mathematical invariants are related will give us insights into non-perturbative physics. Okay, so here's just to give you a flavor of what mirror symmetry is doing. So what's underlying mirror symmetry is an isomorphism of two types of string theories. So there is a 10-dimensional string theory called type 2A, another one called type 2B. You can think of these as initially being defined by sigma models, namely maps from 2-dimensional Riemann surfaces into a 10-dimensional space, where a real 6-dimensional manifold are Calabi-Yau manifolds, Calabi-Yau threefolds, so complex 3-dimensional times Minkowski space, and then there is totally different sigma model mapping into a totally different 10-dimensional space. And there is an isomorphism on the level of the formulation of this initial theory. Another place where you see this isomorphism is that looking at this sigma model or the other one, you get identical physical theories in 4 dimensions. So these remaining 4 dimensions which we live, you wouldn't be able to distinguish, you wouldn't be able to know which 10-dimensional theory you came from. So whatever you have in intermediate steps on this manifold should have counterparts here, because eventually you're not able to distinguish these. So I told you before, motivation is to think about theories and geometries in terms of parameters, so all families. So where does this come in? It turns out that the initial formulation, this 2-dimensional, there's some algebra here which admits a natural moduli space. And in terms of the formulation, this moduli space translates into a space of deformations of these Calabi-Yau manifolds, which is, however, very different on the two sides. So on one side, this deformation space will be related to the changing the volumes, and the other one would be changing the complex structures of the underlying Calabi-Yau threefold. And even this side here is crazier than just changing the volumes, because it will also, the mirror symmetry would predict that this space may also contain several different topologically different Calabi-Yau manifolds, and sometimes it's also very difficult to think about certain points here in terms of a geometry. But there is a notion of a complex moduli space here, which matches a classically well-known moduli space of complex structures. Okay, and so of course this equality. So what is being equal? So I mentioned to you, okay, there's many ways of how you can formulate this. One thing is the data of the remaining 4-dimensional theory will be identical. On the level, on mathematical level, why is this interesting? Is you have a matching of the moduli spaces. So if you pick the correct coordinates on both sides, you can match local coordinates. But there is more you can match. So actually what you can match is the data of a flat connection. So there is a whole system that you can match on both sides. And this became really interesting in mathematics, because here the data of this flat connection was something that was classically very well studied. And part of what you obtained here gave you in one shot generating functions of enumerative invariants here that were very hard to compute otherwise. Can go one step further. So apart from mapping or identifying the flat connections that I just mentioned here, there is a geometric quantization problem that you can associate to both sides. And there is a natural, or there is a notion of wave function or a state in a Hilbert space of this geometric quantization. That's the way I would like to introduce or think about topological string theory. So you should just think of this as something that you can obtain from the data of these underlying matching moduli spaces as well as flat connections that you have. The topological string partition function is like a real or like a physical string partition function. It's given as an asymptotic. So this is the exponential of the free energy, and the free energy is given as a formal sum with a formal parameter lambda, which is the topological string coupling. And this formal sum is asymptotic. So these FGs, the free energies at genus G, grow factorially with G. And this will depend on a local coordinate on the underlying moduli space. So you typically have a topological string partition function for the whole family of underlying theories. And then you have the topological string partition function or the construction on both sides of mirror symmetry. And then mirror symmetry becomes a matching of these topological string partition functions. This becomes interesting mathematically because on one side, which is the side which is more difficult to formulate in terms of math of the underlying moduli space, this topological string partition function encodes the generating functions. So the free energies at genus G will encode an infinite, generically infinite set of rational invariants, which are called the Gromov-Witten invariants at a given genus G. And there is another summation over beta, and beta is a class of a curve of the underlying Calabi-Yau threefold. So conjecturally, this free energy of topological string theory will give you in one generating function all of these data. One thing that I should mention, so explicitly these Gromov-Witten invariants, the parameter of the underlying moduli space T appears periodically. So it's already a Fourier type expansion here. So those will be important when I talk about resurgence later.
Sorry, but you're summing with infinite lattice there with Q as well, right? So then that's a formal expression in Q?
It's a formal, yeah. So generically you will have, yeah, so you're summing over the lattice, which is H2 of the underlying manifold. And you'll have, generically, you'll have infinite. And so these, yeah, exactly. It's doubly formal from the point of view of Gromov-Witten theory, but from the point of view of topological string theory, these Q are really just exponentials of local coordinates on the underlying manifold. So there, it's really, you can think of these as functions of T, right? So it's functions of T expressed in a certain limiting point. Yes, but exactly. So from a mathematical point of view, is it just a double? Yeah. So depending on how many betas you have, it's formal in lambda, it's formal in Q. There is no reason why, this is precisely what I mentioned in the introduction, there is no reason why different mathematical invariants should be collected within functions. And how these things are organized in terms of special functions, that's sort of early days of mirror symmetry known. This is really the data of the flat connections. The new piece is that even the lambda is not a formal variable, but you can really think of this as a complex variable of an honest multi-valued function. But this is only recent. This is something you can obtain by resurgence. Okay. But thanks for the question. Yeah. So a priori both look formal, but both of them, so both types of variables become variables of special functions. Okay, so this Gromov-Witten potential, the free energy, can be furthermore decomposed into a constant piece, or a piece of constant maps, which has a universal form for any Calabi-Yau manifold. And then there is a non-constant piece, F twiddle. And there is work of Gopal-Kumar and Vafa, where this asymptotic non-constant piece, so everything that has a Q in here, can be reorganized in terms of this expression here. So here you see that the asymptotic lambda summation got replaced by this factor, including the sign. So then you can ask, okay, is lambda a formal variable? Was it real? Now it all of a sudden, it's not an asymptotic series, but it has infinitely many poles. Or can I really think of lambda as a complex variable and this as some sort of meromorphic function with infinitely many poles? And this is one of the things that I want to address in this talk. Okay, so mathematically, the way after the early days of mirror symmetry, where this matching of flat connections, the conjecture that was formulated due to Kontsevich is that actually what is being matched, because it was a complete mystery why there is two pairs of Calabi-Yau manifolds, what is exactly what they share. And mathematical conjecture is that there is a category, so a collection of objects associated to one side or one Calabi-Yau manifold that should be matched with a different category for the different object. And the types of objects are, in this case, objects naturally studied within complex geometry. On this side would be objects studied within symplectic geometry. And here you may ask, okay, what happened to this underlying moduli space that I was advertising earlier? Here it seems that just you take the spaces and then you just match object by object, and there should be, and this has been proven for many cases that there is this isomorphism. Like really, you can construct for a mirror pair these isomorphic categories, and you can match object by object. But what happened to the moduli space? So why is this not a statement of families? The statement of families comes in again and guided by intuition from mathematical physics, is that actually you do not care about all the objects in these categories, but you physically you would only care about a special class of these objects. And these are called Bps objects. So Bps is a physics terminology telling you it's a certain bound on the mass of a given object with charge gamma at a particular point in this moduli space. It's a bound from below given by a complex number that you can calculate only if you know the charge of this object. So every object in a theory has to obey this bound, and there is a special set of objects that saturate this bound, where the mass is equal to the absolute value of something that you can calculate only from the charge. And of course, since we're considering families of theories, the mass and the central charges change as you move around the moduli space. So they can become massless, they can become very heavy, but it's always such that this bound is saturated. And sometimes you have objects that are secretly composite, so they really have where the charge can be further decomposed. And sometimes they exist as a single, so as an object on its own, which saturates this bound, and sometimes they do not. And this is exactly where this wall crossing phenomena comes in. And the wall crossing on the level of these categories or matching objects is given in terms of a stability condition. So for a given charge, if you want to consider whether a given object is there or not, this is told by a stability condition, which was formulated using sort of genus zero mirror symmetry by Douglas, Fjoll, and Römersberger, and then abstracted mathematically by Bridgen. And what you should match then is stable, what are called sheaves on one side with special Lagrangians on the other side. And there's a set of invariants on both sides, which are both called Donaldson-Thomas invariants, which would tell you, so they're either zero or non-zero. And when they're non-zero, then this object exists as a stable object. And when they're zero, then it doesn't exist. So there should be some generating function again. So if we think of in terms of the way to organize these new sets of invariants is again in terms of some partition function, then there should be a partition function of Bps states. So just a given theory, introduce labels, and then give some data which will tell me which Bps states are there or not. And this should match the mathematical generating function. And then the question is there any relation between the set of mathematical invariants that you obtain perturbatively from a physical point of view and the ones that are intrinsically non-perturbative? And this relation has been long expected. So both in math, these people conjectured a relation between the Gromov-Witten partition function and a Donaldson-Thomas partition function, which has been proven in an infinite set of examples just by changing variables here. Physically, what this corresponds to is that the topological string is a perturbative formulation in the string coupling, and Gori, Strominger, and Waffa conjectured that this should be related to a black hole partition function. So to a given string theory, all the objects that can live on the Calabi-Yau can form black holes, and there's a statistical physics generating function which you can attach to this one. Okay, but there's been lots of difficulties in making this relation precise, and also this relation here only holds for certain types of Donaldson-Thomas invariants. There's been a lot of progress more recently in the last 5 years, which is also what triggered in large part my own work on this. And that's work of Tom Bridgeland, who took works of Gayotto, Moore, and Knightsky on wall crossing phenomena, and in particular, a particular conformal limit, which also appeared in a talk of Professor Ito yesterday. And just taking this problem, okay, you have a set of special objects, and this is their wall crossing structure, and formulating a Riemann-Hilbert problem, okay, is there something that encodes all of this? And this is what's called a Riemann-Hilbert problem. What he found is that there is a notion of a tau function which knows about all these wall crossing structures. And surprisingly, the tau function expanded in a certain region in its parameter space, gave in Bridgeland's work the asymptotic series which encodes the Gromov-Witten invariant. So that was the reason why in Bridgeland's work this tau function was considered to be a candidate for the non-perturbative completion of topological string theory. What I want to talk about today, okay, if there is a way to get from wall crossing structures to non-perturbative topological string theory, could you start with just the asymptotic series and still obtain information about the Bps structure and the wall crossing structures? And this is yes, so not in general, but in generic, so in a building block type of example. Okay, so now let's move on to non-perturbative topological string theory. So topological string theory is very interesting. So physically, because it shares many features of physical string theory, but it's much more computable. So as we've heard in the last talk, it's no problem to obtain higher genus free energy. So this is true for a class of examples, but this is already much better than physical string theory. But it's also very interesting because there's many dualities to other problems in mathematical physics, namely matrix models, Chern-Simons theory. And there's been a lot of work on defining non-perturbative topological string theory in using all these relations. So with many authors, some of whom are present, is using, so if you know matrix models and if you know non-perturbative corrections there, then you can transport this for the class of geometries that have these correspondences. There's been a lot of work on defining non-perturbative topological string theory for an infinite class of non-compact Calabi-Yau geometries using spectral theory. So there's some underlying quantum mechanical problem which puts forward natural candidates for the non-perturbative completion, and from superconformal theories and so on and so forth. What I want to address today is, however, okay, what if you just have topological string theory with the asymptotic series as an input, and without going through dualities and through other things, is there a way to address this more intrinsically? So just from the data that you have. And there's two routes to this that I want to talk about. So one thing that I have been trying to work on is really trying to derive some differential equation in lambda. So the power of early days mirror symmetry was really from obtaining the flat connections, which can be translated into differential equations. Once you have the differential equation, you can find special solutions. And I was trying to find something in lambda, and that's in some work. So the asymptotic expansion of topological string theory has some recursive structure. What we're able to do is find some universal limit within this recursive structure that gave some airy differential equation, which was already hinting at some non-perturbative structure behind this. More recently, however, I came back to this problem, and in a particular case, I was able to derive some finite difference equation in lambda. And then what you will see is that the finite difference equation is derived from the asymptotic series, but solutions of the finite difference equation are analytic functions in lambda. So these will be natural candidates for the non-perturbative completion. But of course, more systematically is using the methods of resurgence and Borel resummation. And yeah, so my goal will be to combine these two things. Okay, so the class of geometry. So this is for the moment the deformed and resolved conifold. So the conifold, so x1 to x4 are complex variables. The conifold singularity refers to the zero locus of this equation in C4. And topologically, this is a cone over the base S2 times S3. And there's two ways of going about changing this singularity. One of them is called the small resolution. This will be algebraic geometrically replacing the origin with projective line. And the other one is a deformation that will be just replacing the zero with a complex, with a non-zero complex number. So both of these were very early instances of Calabi-Yau, non-compact Calabi-Yau threefolds, where it was possible to obtain all genus results. Again, using dualities to different string theories and Chern-Simons theories that were there. So I'll just focus on the small resolution, and this is known as the resolved conifold. So the origin gets replaced by a projective line, which is the same as an S2. And then it's a rank 2 bundle over this. So it's a non-compact Calabi-Yau threefold. The parameter T, which parameterizes the underlying moduli space, is an integral where the imaginary part is the Kähler form of the P1. And then there is a real part, and this is physically called the B field. The all genus result was obtained by Gopal-Kumar-Baffa using a duality with the Chern-Simons theory, and it can be written in this form. So this is the asymptotic series, and it's entirely given in terms of these Pauli logarithm function in terms of the variable q, which is again exponential 2 pi I t. Okay, the Gopal-Kumar-Baffa resummation in this case. So in general, you would also have some. So here there is a 1, which is not spelled out, and it's the only Gopal-Kumar-Baffa invariant that is there, and there is no summation over higher genus Gopal-Kumar-Baffa invariants. So although there is infinitely many Gromov-Witten invariants, because at every order this thing doesn't vanish. After the resummation, there is only one non-trivial invariant here. Okay, so what I was able to derive really just from the asymptotic series, and here I was really guided by a paper of Iwaki, Koike, and Takei, who derived a similar equation for free energies of the Weber curve using topological recursion, which just as a comment, that will be the free energy of the deformed conifold. So the other direction, which I didn't mention. But it turns out that there is a very similar difference equation with very similar techniques that can be derived, which now mixes the dependence on the underlying moduli space as well as this formal parameter. This check is really just a normalization by 2 pi. And here the surprise is really it's an inhomogeneous equation, and on the right-hand side you only have something at genus 0. Okay, so what's the benefit of having an equation after you already had the solution? So it was derived knowing the complete solution, so it may be useless. So one benefit is these types of equations generalize Toda equations, so it relates to integrable hierarchies. This is something I won't talk about today. Should also mention a similar difference equation in Gromov-Witten theory was previously conjectured for the case of Gromov-Witten theory on just P1 by Rahul Pandaripanda, again motivated from matrix model physics calculations. Okay, so that's one benefit. Another benefit is if you know that the asymptotic series satisfies the equation, you can also look for better, so really actual functions in lambda, which satisfy the same equation, then ask yourself whether these would be the non-perturbative functions that you want. And it turns out that there is a function like that. So this is related to what's called the triple sign function. This is just one particular representation. In order for this representation to hold, you have to restrict the parameters, but it's more general than that. So if you have different sets of parameters, there will be different representations. I just wanted to present to you that it's really not, yeah, or at least it looks like not a very difficult function. And this triple sign function has been around in many different contexts before. So it turns out that this thing here also satisfies the same difference equation, and it also has the same asymptotic expansion as the one you started with. So this would be the candidate non-perturbative free energy. And you can look just here, you can explicitly, so this contour is along the real axis, avoiding the origin. So you can explicitly look at the residues of this expression, and then you'll get some resummed expression. And if you write this up, then you will find this piece here, and then also another piece here. The first piece you can easily recognize, that's just the Kupa-Wafa resummation. So this is sort of the minimal resummation of the asymptotic series that you had. But here there is infinitely many other things, and all of them are exponential of instant on some action divided by lambda. So this is precisely the type of non-perturbative effects that you have, and you have infinitely many of these just packaged in this form. And this form exactly matches computations that were around earlier of Hatsuda, Okuyama, using modified Borel summation. And it also matches a general structure that was expected in the program of Marcos Moreno using spectral analysis. So then you would say, okay, this is the non-perturbative completion of topological string theory, we're done. Which is not quite true. So this is a non-perturbative completion, and this is something that you can now systematically address using resurgence techniques. And this is what I did with Jörg Teschner, Iván, Tulli, and Arpan Saha, is just taking the asymptotic series again as your main input and going through the Borel series. So again, we've seen this a couple of times. So here the asymptotic series is near 0. The Borel transform using the convention where you just shift the n by 1. And what will be important for me is using as the inverse of the Borel transform the directional Laplace transform. So in general, I'll also allow here certain complex phase in order to get to the Borel sum. So the Borel sum will depend on the direction in the complex Borel plane. So what we did is really taking this asymptotic series as an input, and then we benefited a lot from techniques used in a paper by Garoufalidis and Kashayev, which were looking at the resurgent structure of the Fadeev quantum dilogarithm function. And there's many of the techniques really were able to transport to this case. And this is then the Borel transform analytically and exactly of the topological string free energy on the resolved conifold. And zeta is now the Borel transformed variable, so what replaces lambda. And you can explicitly see the types of poles that the Borel transform has. And you would see that there's doubly infinitely many poles. So both m and k are integers. And yeah, so this Borel transform matches also. So there's a different but equivalent Borel transform given more than 10 years ago by Pasquetti and Schiappa. In the context of studying matrix models, you would also find that this resolved conifold can be formally thought of as an infinite sum of just the Gaussian matrix model, where you have the analog of this integer shift here. So anyhow, so these infinitely many singularities, so the m and k organize in this way. So if you look at the Borel plane, you'll have infinitely many Stokes rays. And on each of these rays, you have, again, infinitely many singularities. So what you can do now is using the directional Laplace transform. So in particular, you can do it along the real axis. So this is for a particular choice of t's. But for every t, you will get just some collection of these rays. And there will be infinitely many of these accumulating to the imaginary axis, both from above and below. So what you can do now in order to define the Borel sum is just pick any ray in the complex plane as long as it's not on one of these complex, on one of these Stokes rays. And so we label these, we call these rho, and just some convention. So we call rho 1 the one between 0 and 1, and then rho k would be the one between the ray lk and lk plus 1. What you can do is then really compute what is the Borel sum and give an analytic expression for that. But you can do more. You can ask, okay, what happens if I compute a Borel sum here? I don't know, what's the difference between rho 1 and rho 0, for example? What's in general the difference between rho k, the Borel sum attached to the ray rho k, and the Borel sum attached to the ray rho k plus 1? And this is something that you can obtain exactly, and it turns out that the difference between the Borel sums attached to the ray rho k plus 1 and rho k is given by this expression here. So you see again, this is given in terms of a dilogarithm, just a special function, exponential of t plus k, and then divided by the parameter, which was your initial formal variable. There's one particular ray, which is anything here and along the real axis or anywhere in this big wedge here, which you can compute explicitly and gives you precisely the function that I had found earlier as a nice solution of the difference equation. But there's also infinitely many other of these. So you can take this result, rho 0, and then do the Stokes jumps infinitely many times, and then you can ask what happens in the limiting case when I reach this imaginary axis. So you can't really start doing the Borel sum there, but you can ask what's the limiting one. And the limiting one turns out to be the Goparkuma-Waffa resummation. So the limiting one is telling you that all this expression here is really just the infinite sum of these Stokes jumps. Okay, what's more? So what does all of this have to do? So I advertise that there is a relation to BPS problems. You can attach each of these rays. So each of these rays is just R minus times this quantity here. And this quantity is what I had mentioned in the beginning of the talk, that will be what you would call the central charge of a given object living on the same Calabi-Yau manifold. So one central charge is a parameter t, and the other one is just an integer k. So every one of these rays corresponds to a charge of a given BPS object. And what appears in these jumps is really exponential of the central charge of a BPS object. And this relation can be made precise by really looking at how this matches Bridgeland's Riemann-Hilbert problem. Turns out that the topological string partition function is really a generating function for the types of objects that Tom Bridgeland is looking at. And then you know that what appears, the prefactor, which was here 1, is really the Donaldson-Thomas invariant corresponding to the singular ray that you've been crossing. And all of them are 1, except the one limiting one is -2, and we're also able to obtain the jump there. So then there you have to work a little bit harder to obtain the jump where this is a -2. So on interpretation, so now you would say, okay, to a given ray in the complex plane, the validity of the Borel sum is in a whole half plane, so there will be generically infinitely many overlapping ones with regimes of validity. And the natural way to interpret this is that really the topological string itself, so that will be the partition function, the exponential of the free energy, is a section of a line bundle. And all these transition functions, the Stokes automorphisms, are transition functions of this line bundle. So in order to get a function, you just have to fix some section. So, and this also corresponds to construction or an expected construction of line bundles in works of these people. Okay, so now let me come to a different part of the talk, namely now once you have the Borel sum, what you can also address is, and especially so there is the one generating function that I showed you, but we're also able to prove a different integral representation of the non-perturbative topological string partition function. And as soon as you have this, you're not constrained to just looking at the asymptotic topological string weak coupling expansion where lambda was formal and small and didn't converge. But you can also look at the inverse of lambda. It turns out to be convenient to have factors of 2 pi. So what you really want to take the inverse of is lambda divided by 2 pi. And then also in terms of the parameter t, it turns out to be natural to take another parameter t, which is t divided by the original lambda. So that will be the transformations like these are what you would typically expect within the context of S duality. So there you can take any of these. So for example, the Borel sum along the real axis, and just having the analytic function, you can expand it in 1 over lambda and in t over lambda. And you get something, again, an asymptotic expansion. So it's an asymptotic expansion now in the inverse of lambda. And it almost looks, so there's a piece which looks like the thing you started with, but there's also other things. So which is telling you that there is a strong coupling version of topological string theory, which also wants to have some enumerative interpretation, which wasn't able to give yet. Anyhow, so you can just now have this dual asymptotic expansion, and with a dual asymptotic expansion, you can again do resurgence and Borel resummation, and you'll find a different Borel resummation problem with different jumps. So the jumps here again across array, which is labeled by an integer k, will be given by this expression here, which you should recognize from maybe the last talk. And also this type of Borel summation relates to studies of what are called non-commutative Donaldson-Thomas invariants, and also in the study of framed Bps states. So this is different jumps of now the strongly coupled version. So you have both asymptotic expansions in the original variable as well as the inverse. And in more recent, in the work with Lotte Hollands and Iván Tulli, what we were able to further derive, so there we looked at many generalizations of this problem. So there is a generalization of topological string theory where instead of just having 1 lambda, there is 2 parameters, which is called the refinement. And there is resurgence in both of these parameters. And there is 2 interesting limits. One of them is the topological string. There is another one, which also appeared in yesterday's talk, which is called the half omega background. And if you look at the resurgence in the half omega background, we're able to relate this to exact WKB. So all of this is nothing that I didn't want to pack too much details into this talk, but this is what we addressed in this paper. And this is one of the byproducts of looking more generally at all sorts of difference equations, is that the non-perturbative completion, or the Borel sum of the free energy, is no longer periodic in T. So although the starting definition, the asymptotic series of Gromov-Witten invariants, was periodic in T, so that would be 0. The non-perturbative completion is no longer periodic, but it has this inhomogeneous term. And in the inhomogeneous term, you precisely see the Stokes jumps. So this is the sort of the connections to difference equations, which is emerging, which I think is worthwhile studying much more. So there's 2 dual difference equations. One of them is shifting the original F asymptotic series in terms of the original lambda. And there the inhomogeneous term can be related to the Stokes jumps of the strongly coupled Borel resummation. And likewise, the difference equation that you would obtain from the asymptotic series at strong coupling have as an inhomogeneous term the Stokes jumps of the weakly coupled version. So there is an interchange of roles of things going on here. And here you would also see that all what used to be non-perturbative corrections from the initial point of view is satisfying this inhomogeneous equation. And the whole Gopar-Kumar-Vafa summation, which from the point of view of the strongly coupled topological string is now the non-perturbative corrections, is completely in the kernel of this equation because it's manifestly periodic in T. Okay, so this is begging for much more explanation. Maybe just let me mention one further aspect of the work with Lotte and Iván, and that's a possible way to interpret this difference equation. So there's been lots of work on difference equations that were obtained in the context of mirror symmetry from what is called quantization of curves. which is something that I won't talk about today. But as I mentioned, there is a mirror of the result conifold. There is some curve, and the curve itself can be thought of as a quantum operator in curve variables, and there is an exact WKB system that you can look at there. And now the question was whether the difference equation now in the closed string moduli also has an interpretation as a curve. And it turns out, yes. So if you take the topological string partition function and take this ratio where you, in one of them, you shift t, then you can write down the difference equation that I gave you before in terms in this way here. So you can call this psi. And psi is, yeah, so you can call this as a certain wave function. And a wave function, if you interpret this equation here as really giving you Hamiltonian in terms of some position variable and the dual variable, which is a momentum, which gets represented by a derivative in terms of t. So there is an interpretation of this ratio of topological strings as a wave function of this curve. So there is a quantization of curve, and so far I don't know what the interpretation of this curve would be in the closed string moduli. And this quantity here is also not an accident, but it relates to a derivative of what's called the Nekrasov-Shatashvili limit of refined topological string theory. But again, this is beyond the scope of the talk, but it relates to what was mentioned yesterday. So then this side here relates to a resurgence study in the context of WKB. Now I should mention the WKB, exact WKB in terms of these exponentially related variables in our paper. We could really obtain all orders exact results and then also do the resurgence analysis there exactly and connect it to resurgence properties of this, not of topological string theory, but of this Nekrasov-Shatashvili limit of topological string theory. Should also mention there has been very related work by Grassi-Howe and Knightsky, which has both overlap with this part connecting resurgence to exact WKB, as well as the original topological string theory. Okay, so let me summarize. So what I try to tell you is that non-perturbative topological string theory can be addressed using differential difference equations. So it's really the formal variables in terms of which you have the asymptotic series wants to be interpreted as hopefully at the end of the day as a geometric modulus, as a local coordinate on some space. And there should be some connection such that there are some equations that you can derive more generally, such that the solutions would know about the non-perturbative structure but admit asymptotic expansions. Systematically, you can address the non-perturbative structure using Borel resummation, and then eventually you also see connections. And after having the non-perturbative structure, you also see dual difference equations, which complement the original ones. And of course, big elephant in the room here is trying to understand what S-duality really means in topological string theory. So this lambda really wants to be, I think, interpreted as a modulus, and then there is a whole modular invariant. So far, it's really just the expansion at small lambda and big lambda, but I think there should be the whole modularity in lambda as well. Okay, so I would like to end with this, and we have some time for questions.
Questions? I already one.
Is there a particular reason to study the resolved conifold as opposed to the deformed conifolds? Like, is that easier, or is there a theoretical reason you chose that?
No. So in my original, so the difference equation, so as I mentioned, the one for the deformed conifold was already there. So in the guise of free energies of the Weber curve, but it's exactly the deformed conifold. And there also the non-perturbative, so the analog of this triple sign function or the special function that has the non-perturbative structure is the Barnes G function. So that was already known, for example, in the context of matrix models. So there, this quadratic curve corresponds to the Gaussian matrix model. So there you have this one, and there you only have, so the analog of these Stokes jumps, you only have one. So there's only one BPS state there, and there's really In terms of the Barnes G function, it's the relation between the Barnes G function at argument z and minus z. Or if you want, in terms of the after one step of difference equation, you get the gamma function, and there is a relation between the gamma function of argument z and of argument minus z, and that will be the analog of the resurgence structure of that one.
Right. Yeah. It's just Iwaki and I kind of did that for several examples.
Yes.
So yeah, I think it's related in some way, but okay.
No, so exactly. So if you want, as I mentioned, so in work of Schiappa and Pasquetti, even the resolved conifold, so what you can formally think of this as an infinite, so it has an infinite BPS spectrum, and you can formally think of this as an infinite sum over Barnes G function. So if you want per BPS state, you get a Barnes G function, except that some of these infinite sums, so if you take the same function with shifted arguments, it's a little bit difficult to make sense of this infinite sum. But of course, in all problems where you have finitely many BPS states, it will be a finite sum over these Barnes G functions, as you've seen in your work. And sorry, so another thing that I haven't been able to think about. So also for the deformed conifold, I think there should be something like that, but it's a little bit more difficult for me, at least now to see. It's the analog of the dual expansion. So what's the strong coupling topological string on this same space?
Yeah. Yeah, I was going to ask. Perhaps I missed it, but is there some physical interpretation of your difference equation from the perspective of like the 5D Nekrasov gauge theory? Like, is it some relationship between defect partition functions or something, or is it not?
So not that I know of, which doesn't mean that there isn't. Again, so what the interpretations that I have looked at with collaborators, one of them is the relation in terms of Gromov-Witten theory to integrable hierarchy. So that's right. One thing. In terms of gauge theory, I don't know. So and then the other interpretation is just writing the same difference equation in terms of a quantization of a curve. But then I also didn't tell you, and because I don't know what the curve is and why it's there, and why now instead of just having a moduli space parameterized by t, you have a phase space, and in the phase space you're cutting out a curve, which is a Hamiltonian. And this is one of the things that I mentioned in the introduction, is that in retrospect it seems that there is quantum mechanical problems emerging, which you don't know why they do. But yeah, so there is probably also a 5D interpretation of what the difference equation is doing in terms of inserting line operators or something like that. But
line operators,
yes.
So you might guess a sort of defect thing.
Yeah.
Cool, thanks.
But this quantization is not the mirror curve of Grassmann.
No, absolutely. So thanks for the question. So the mirror curve, so let's say has variable y and x, and these are open string variables. So that will be the parameterizing the open string moduli. So the curve here is really a different curve. So it's a curve in the moduli space. So sorry, not in the moduli space. So a priori you would double the moduli space. You would say the original moduli space was just complex one-dimensional, but now it looks like you have a two-dimensional phase space and you have an algebraic curve in exponentiated variables inside there. So that should be some Hamiltonian. And yeah, so the Hamiltonian is really governing. So the wave function of this Hamiltonian is this. It's exponential of the Nekrasov free energies. And these are, yeah, so since we were talking about this earlier, so these are the things, or the analogs of the dt derivative of the Nekrasov partition function. Should eventually relate to what in the previous talks were the rho 0 and rho pi. So these exponentials of something, and here the leading order of this is really just the classical periods on the curve, but there is infinitely many lambda corrections, and you can really think of this lambda here as an h bar and as a quantum mechanical problem, which gives you h bar deformations of the classical periods. Yeah, and these would be the things. If you look, yeah, so this is what we did in the work with Lotte and Iván. If you really look at then now the Stokes jumps of this object here, then it's precisely of the form log 1 minus exponential of t divided by lambda. So this has the same Stokes jumps as the objects that appear in this plan of A. The topological string has Stokes jumps in terms of the dilogarithm, and you can think of this as sort of a generating function of these things here. And it's precisely, so this thing here is obtained, you can think of this as really one step of the difference equation. So difference equation has two terms and is already taking one step. And after one step, you obtain the things that have Stokes jumps, which are only logarithms and not dilogarithms.
Let
Yes.
me ask. Yeah. I think the TBA-like equation for topological strings constructed by Alexandrov. And how is that kind of formulation is related to your?
So yeah, so now I can, please, this is going to be on the internet forever, so I hope I don't say anything wrong. But the way I understand this, the TBA equations of, so first of all, all of this is related to work of Gayatò-Moore and Knightsky. But for the moment, it's only related to what Gayatò calls the conformal limit. So the work of Gayatò-Moore and Knightsky has a whole twistorial structure, but there is some sort of holomorphic slice in there, which connects to Bridgeland's Riemann-Hilbert problem, and then also to this resurgence thing here. And the TBA equations are really what you would think from the wall crossing problem, that's the starting point, or this is a formal solution of the wall crossing structures of some torus coordinates. So then there's an underlying electric magnetic charge lattice, and depending on the rank of the lattice, you want to construct a number of coordinates, and you impose sort of the wall crossing structure, and this leads to the TBA equations. From this point of view, or at least in this case, what we understand now is that the topological string itself generates all these coordinates. So in this case, there is only two coordinates. One of them is precisely this one here, so it's exponential of dt fns. And the other one is really just exponential of t divided by lambda. So there's two dual coordinates, and these would be the solutions of the TBA-like equations here. So more generally, it's hard because it's coupled. So here it's really one of the two coordinates doesn't receive h bar or lambda correction. So t just remains to be t, and there's no asymptotic series and lambda that corrects it. And then only one of them gets corrected infinitely many times. But generically, it would have corrections in both, and that's why the TBA equations are coupled. But in general, you would also, from Bridgeland's approach, expect that both, so even if it's coupled and everything is coming just from one common tau function, which should be then related to the topological string partition function.
Any other questions, comments? If not, let's thank Murad.